Hey, Mr. Harridan here. We're going to do another video for combined gas laws. Me and Darian, we're here to help you out here. Right, Darian? Right. If the pressure of a gas in a rigid container changes from 800 torr, so pressure 1 is 800 torr, to 11 psi, 11.0 psi, that is pressure 2. At the lower pressure, I gotta figure out which one's the lower pressure here, so we gotta do a pressure conversion here. So I'm gonna convert uh, 11 psi over to torr, okay? Or I could convert it to torr to psi, it doesn't matter. Psi on the top, psi on the bottom. What are we going to convert to? Torr. Swish, swish. This is 760. This is 14.7 according to the formula chart. We're going to solve that. And we get 568.70 torr. So we're going to cross this number out and put 568.70 torr. So now I know that the lower pressure is 568.70 torr. The temperature is found to be 40 degrees Celsius. You're right, Darian. We cannot use Celsius. We have to use Kelvin. So 40 plus 273 would be 313. And this is at the lower pressure, so this is T2 is 313 Kelvin. How many degrees Celsius did the temperature change? Well, that's a tricky part right there, temperature change. As the temperature dropped. So this is going to be T1. This is one of the trickier problems here, actually. And we're going to find that in Kelvin. Okay, so we're going to write down our equation here. P1 V1 over T1 equals P2 V2 over T2. Volume is not mentioned in this problem, so we are going to cross out the V's. Okay, so we're going to put into our number here 800 torr T1 equals 568.70 torr 313 Kelvin. So notice that the pressure is dropping here, so the temperature should drop. We know this is Guy-Lussac's law. Remember, he's French. He really is French, so you know. Okay, to solve this here, you're going to multiply these two numbers, because that's where you're going to cross multiply and divide this number. Okay, and then we get a T1, which is equal to, I have no idea. Time to look at my notes. 440 Kelvin. Okay, not the answer. Okay, so now we have to figure out the change in temperature, which is T2 minus T1. Okay, so you are going to take 313 kelvins minus 440 kelvins, which equals negative 127 kelvins. But you must be saying, Mr. Harridan, Mr. Harridan, Mr. Harridan, Mr. Harridan. It says the temperature changed in Celsius. Okay. You got me on this one. So I can change 313 Kelvin back to Celsius, which is 40 degrees Celsius. And I can take 440 Kelvin and subtract 273, which is 167 degrees Celsius. You subtract 40 from 167 and you get negative 127 degrees Celsius. That's the correct answer. Remember, back in chapter 2, we said that the change in temperature in Kelvin and Celsius is the same. So really, I did not need to convert that one back to Celsius. If I'm looking for the change in temperature, you can just subtract the Kelvin temperatures. And it's always T2 minus T1. It's always final minus initial. Good law for physics here. Okay. Okay, I know that was a tough problem there, but we got it done, so good job. Okay. What happens to the volume of a gas if the pressure increases 2.41, so assuming the temperature remains constant? Everybody's like looking at this problem and going, what? Where's the numbers? Well, here's the thing. You get to make up the numbers. This is like a key Harridan strategy here. This is what we call the Harridan law of ones. It works in physics too. So, what happens to the volume of the gas? So I'm going to look for the volume of a gas. I'm going to put in liters. Okay? If the pressure increases 2.41 times, so I'm going to have a pressure 1, I'm going to have a pressure 2. To make my math easy, I'm going to use pressure 1 as 1 atmosphere. So if it increases 2.41 times, I know that pressure 2 is 2.41 atmospheres. Okay, we're assuming the temperature is constant, so we need a V1 here. So to make my math easy here, I'm going to use 1 liter. Check my units. Okay, I made them all the same. I'm smart like that. Okay, we're going to write down our equation. P1 V1 equals P2 V2. Okay, we're going to use 1 atmosphere equals 1 liter, which equals 2.41 atmospheres, which equals V2. Okay, remember this is P1 V1 equals P2 V2, so if the pressure goes up, the volume should go down, correct? Because this is Boyle's law. Because he's the only one that came up with an inverse law. Okay, so we end up multiplying these two numbers, correct? And then we are going to divide by that number. And I get a pressure of, not pressure, volume. Hello, Mr. Harridan. Pay attention. V2 is equal to 0.414 liters V2. So the volume does decrease. Thanks, Darian. You did an awesome job on that problem too. One more problem in this video here. What happens to the volume of a gas if the pressure is tripled and the Kelvin temperature is doubled? Where's the numbers? There is no numbers here, so we're going to use the Harridan law of ones. What happens to the volume of the gas? So we're going to figure out V2, which is going to be question mark, liters. Okay, so my V1 is going to be 1 liter to make it easy on myself. If the pressure is triple, so P1 is going to be 1 atmosphere. P2 is going to be 3 atmospheres. And this Kelvin temperature is doubled. So T1 is going to be 1 Kelvin. That's really cold, but whatever. Shouldn't matter. And then T2 is 2 Kelvin. Check the units to make sure they're the same. Okay. They're the same. Write down my equation. P1 V1 over T1 equals P2 V2 over T2. Vice President sits on top of the table here. So this is going to be 1 atmosphere times 1 liter over 1 Kelvin equals 3 atmospheres V2 over 2 Kelvin. Again, we're going to do the cross multiply thing here. So V2 is here. So we circle the 3 that are opposite of this. So you're going to multiply 1 times 1 times 2. And then you're going to divide by 3, and you're going to divide by 1, which gives you a V2 of 0.667 liters, which means the volume went down by a third. And this is the combined gas law. Okay. Okay. You guys are champions. The legend is out.